We are live.
Hello, everyone. Welcome to this 110 Latin American webinar for physics. It's a pleasure to have today Dan Carney, who will talk to us about testing quantum gravity in the lab. Dr. Daniel Carney, he studied his PhD at the University of Texas at Austin. And then after that, he worked as a postdoc at the University of British Columbia and then at Fermilab and the University of Maryland together in a joint position. And today he has actually the title that many of us always want. He's a scientist at a Berkeley lab, and he will tell us how to measure quantum gravity today. Welcome, Dan.
Yeah, thanks, Walter, and everybody for the invitation to give the talk. I'm very flattered and honored to do this. It's 8 in the morning, so I'll be drinking coffee a little bit at the beginning. I hope you don't mind. So I should share my screen, I guess?
Yes, please.
All right. So, yeah, so as Walter said, I'll talk about testing quantum gravity in the lab. And I think the title often, gets people very emotionally excited because it sounds crazy. So the first thing I want to do is go through and just say what exactly I mean at sort of a very high level. So my origin in physics is actually at the same place as Walter. We did our PhD together in Texas in a string theory group. And so I'm really a high energy physicist in my soul. So if you want to think about quantum gravity, you can think about it in terms of the energy density you're interested in. So string theory or loop quantum gravity or asymptotic safe gravity, or there's other possibilities. These are models of the quantum behavior of gravity at extremely high energy densities. So here I actually gave a number just to point out how insane these densities are. So this is 10 to the 123 electron volt per centimeter cubed. That's the scale at which things happen that are like black holes randomly start forming because there's too much matter around, and we have a breakdown of all of the equations other than the ones of, say, string theory. And this is a very nasty problem. These are very hard things, and it's one of the deepest questions in physics. What is the correct model of gravity at these high energies? And so people have been working on that for, I don't know, 100 years, if you want to think about it that way. Certainly intensely working for 50 years. In this talk, I want to focus on a very low energy question. So much, much lower than these kinds of energy scales. And this question sort of underlies all of these high level questions, the high energy questions in some way. So at low energies, you could even ask this question, is gravity quantum in the first place? And so, sorry, there we go. So is gravity quantum at all? So all of these high energy models like string theory, they all assume kind of from the beginning the fact that the gravitational field itself should be treated quantum mechanically. But what's the reason we think that that's the case? I mean, we don't actually have some piece of direct experimental evidence for that. It's sort of the simplest model if you have certain, prior ideas, like quantum field theory describes everything. But you'd like to be a little more, experimentally hard-nosed and say, okay, why, can I do an experiment that would tell me for sure that gravity is itself quantum mechanical? If the answer is yes, then it means that all of these questions at high energies are, continue to be worth asking. You might, though, be surprised. You never know. Gravity is a strange force, and people have certainly thought that maybe, even at low energies, quantum gravity could be, something quite different than what you might think in terms of, say, gravitons, perturbative general relativity. So I list some options people have talked about. There are options where gravity emerges from some kind of thermodynamic limit of some microscopic thing we don't know. There are even crazier ideas, like Roger Penrose has suggested that gravity will cause wave functions to collapse in quantum mechanical systems, even at low energy. And so broadly speaking, what I want to talk about is testing some ideas like this at energies that we can actually achieve in a lab. And this is a really just a tabletop lab energy. This is not the LHC, which would be another 10 or 20 orders of magnitude higher, but still way below this far ultraviolet string scale. So this slide is like my personal history into this question. So is gravity quantum? So this is the question I'm really going to focus on. And I started thinking this way at the end of my graduate school career, because Freeman Dyson here wrote this great paper, and the title is a graviton detectable? And I thought, this is such a nice question. So can I even know that the graviton exists in a very direct sense? Just find one. Okay, and Dyson's answer to this question is no, you cannot detect a graviton. So you have to be careful about what exactly it says. What exactly he says is, he asks the question, can I build a gravitational wave detector, like LIGO, but scale it and make it so sensitive that it would actually click when a single graviton of the appropriate energy goes through it? And Dyson's answer to this question is no. The argument is that if you take sort of a LIGO type detector and you sort of rescale, how big is it, how much laser power and so forth, it's always going to have so much power, so much energy density in a certain radius that device itself will collapse to a black hole. Or it'll have to be the size of the universe, or some horrible scale that just means this is not an answer about in practice. This is really in principle, the answer looks like no. That said, it does rely on the LIGO type detector for a gravitational wave, but okay. So I actually got quite depressed when I read this paper. I thought this means that I'll never know if gravity is quantum mechanical and I can't test it. But a couple of years later, I sort of started reading a little bit more about quantum information theory. And this is a picture of John Stuart Bell here, who really, I think made a lot of this stuff concrete. And I realized you can ask a different question than, can I detect a graviton? You can ask, can the gravitational interaction do something uniquely quantum? This is what a Bell test asks. Bell's test, Bell's inequalities. What they ask is, can I have, say, two spin half particles and in some state, and some property of that state can only be described quantum mechanically? It cannot be two coins, classically sitting around getting flipped. It has to be something uniquely, weirdly quantum mechanical. So we'd like to ask the question, can you do something like that with gravity? And the claim in this talk is going to be that, yes, you can ask this. Yes, you can do such an experiment. And then, yes, it will tell you something interesting about these sort of more high energy questions about gravitons, for example. So with that sort of intro, the rest of the talk is set up as follows. So I'll talk just by starting about some experimental scales. So this will look very different. I'm going to show some pictures of actual things in labs. I just want to show you kind of what scales to think about and how this stuff could be possible at all. Then I'll move into a quick discussion of the basic theoretical ideas, sort of riffing on the introduction. Then I'll talk about two experimental implementations that have been proposed. So one that was a few years ago now, and one that we recently put up on the archive. And then finally, I'll go back and I'll sort of try to connect what I've shown you to these sort of more fundamental questions, if you want, about graviton, strings, and so forth. So I want to emphasize, since I believe the audience does not say all gravitational physicists and such, that the amazing thing that's happening in the world right now that is driving me to even think about this kind of thing is this emergence of what we would call macroscopic quantum coherence in laboratories. So this picture on top is the Google Sycamore quantum computer chip. The thing on the bottom is the mirror at LIGO. Okay, this thing has, I don't know, 50 qubits on it. It's very small, although it's maybe a centimeter on the table. The mirror LIGO is 40 kilograms. And what's quite remarkable is that both of these objects behave quantum mechanically. And you really have to worry about their quantum mechanical properties when you use them. So that's obvious probably in the quantum computer. In LIGO, the statement is that you measure motions of the mirror at a size actually about 100th the scale of the vacuum fluctuations of the mirror. So you're really talking about quantum behavior in these very large systems. And that's the kind of thing we're going to need to be able to do a test of gravity, because obviously gravity only works at sort of large masses. So to give a sense of how large and what kind of scales we're going to be thinking of, this is a simple sort of figure of merit cartoon. So let me show, this is two masses, let's take them to be the same. I separate them at some distance, and what I'm drawing on the left with these two balls is, consider the mass, this left mass being either in this one position or this other position, separated by some small distance. And now I can ask, so if I just took this thing, put it in the Schrodinger equation and ran time evolution, I can ask, what's the phase of the wave function picked up between these two masses? More importantly, what I can ask is, what's the difference in the phase between this mass being on the one position or the mass being on the other position? This is an easy calculation. You just plug the Newton potential into e to the IHT and calculate it. And what you'll find is that the phase difference, has a simple looking formula. It's got a g Newton, it's got the mass squared, it's got d squared. So, there's the Newton force. And then there's some factors of positions and times to make the thing into a phase. The phase is sort of order 1 with reasonably sized objects. So I put in nanogram masses, I put in micron distances, and I put a second for the time that you run this. So you can obviously move these numbers a little bit, but the basic statement here should be at these sort of, tiny but macroscopic scales, nanograms, seconds, stuff like that. That's when these types of low energy quantum gravity effects, if you want, will become appreciable. This is the scale at which I can actually measure the relative Newton potential between these two masses. There's a nice conversion factor not everybody knows, and I like to emphasize it, that there's a m squared here, and it's in units of g Newton. So in high energy physics, we would call that the Planck mass. And the Planck mass is about the order of 1/100th of a milligram. So people often think the Planck mass is some very super high energy scale, but in a way of looking at it, it's actually a very terrestrial scale. This is like the mass of a typical salt grain. And that sort of underlies why this could be, doable. So some experimental systems where this would be relevant. Okay, so I just show some pictures to show that there's many options, but typically what these are mechanical systems. So this is a mirror hanging on a string that can swing, just like a mirror in LIGO. This is a drum head that can vibrate. It's on a chip. This is a picture of a little dielectric bead that's levitated by an optical field. And all these devices and a number of other devices are basically designed to operate as very sensitive force detection sensors. So this one, I showed the numbers just to, again, emphasize these scales. So this is an actual device, and what it's designed to do is measure milligram scale objects through gravity at sort of millimeter distances. And numerically, just to give a sense, the Newtonian force at those scales is about 10 to the negative 17 newtons. And these kinds of devices pretty routinely now achieve sensitivities to forces at the level of 10 to the negative 21 newtons. Per root hertz means it takes 1 second to resolve that. So you can actually resolve a force much smaller than that now in these high-level optomechanical systems. Okay, so now back to the theory. So I want to explain exactly what we want to test. So this is probably the hardest part of the talk. If you haven't really thought this way before, it's a bit novel. Okay, so what do we want to test? So I keep my picture of Bell here to emphasize how we're thinking. We're thinking like a hardcore quantum person. Okay, so we ask the question, is gravity quantum? So a more concrete set of questions would be, can the gravitational field be put into quantum superposition? Is there a wave function for the gravitational field? Can I do all the usual things, put it in superposition and so forth? This is actually the same question under standard assumptions about quantum mechanics, but you can think of them as different more generally. Can the gravitational field be used to entangle two quantum systems? So I like to think of the second one, and that's a sort of very concretely testable question, and that's sort of what we'll focus on. So what this would mean sort of pictorially is shown here. So what I imagine is I have some source mass, this big ball, and schematically I'm going to draw these wells. So this means the metric field, the gravitational field sourced by this massive object. So this is space-time bending here a little bit because this mass is around. And I prepare this thing in some definite location, and I prepare a probe in some definite location. And now the kind of experiment you want to do is you would take this mass and you prepare it into a Schrodinger's cat state, where it's not in one definite position, but in the superposition of, say, left and right. Okay. And so under normal assumptions about how gravity would work, you would think that then the metric, the gravitational field itself, would also be superposed. So you'd have a state, if you're familiar with quantum, Ket notation, where the mass is on the left and the metric, the gravitational field is on the left, plus the mass is on the right and the gravitational field is on the right. So in some sense, we're testing whether this is true. Does this actually happen? To do that, you actually have to think a little harder, which is, how would I even know that this happened? Okay, then I have to ask the question, how does this little test mass respond to this superposed gravitational field? And that's what's in this third cartoon. So if gravity behaves quantum mechanically, and I'll be a little more concrete later, what you would expect is actually that this test mass will become entangled, with the source mass. So if the source mass is on the left, the test mass will go to the left. If the source mass is on the right, the test mass will go to the right. And so the total evolution of the wave function of the universe in this little picture is that the two masses branch. There's a branch where everything's on the left, and there's a branch where everything's on the right. And this is a canonical entangled state in quantum mechanics. So what we're asking is the right description? That's one way of thinking about this. So why would I care about this? Okay. So just to give a sense of what this can test, so the answer to these questions is, if the graviton exists, the answer is yes. And this is maybe not the first thing you think, but it is simple to work out, okay? So this is a Feynman diagram where I have matter, and the matter is exchanging little gravitons. So there's just little space-time ripples flying around. At low energies, that looks like exactly like the thing I just showed you. It looks like a Newton potential that puts some interaction between the two masses in the picture. This can generate entanglements, and so you can go forth and look for a Bell violation in an experiment with two masses. Just to give a simple counterexample, people have long used equations like this. So this is the Einstein equation, where on the left you have space-time curvature, but on the right you'd have the quantum stress energy tensor of all the matter. But you put these little brackets, which means you take the expectation values. So now on the right side, this is a classical object. This is just the average energy density in the universe. And it's pretty easy to work out that if this is actually the equation for the universe, then because this is an averaging operator, it can't actually see details like the superposition of the mass. Okay, so in fact, in this model, you will not be able to entangle two masses through gravity. So this gives you a setup for the experiment. There's two clear options if you want, and you will rule out one or the other. Okay, so now I want to get a little bit more into how the experiments actually work with this sort of overall picture. I'll talk a little more about these detailed models at the end. Okay. But how would you actually think about doing an experiment like this? Okay. So the first thing you have to know is a little quantum information theory, which is, okay, I'm testing, are two things entangled? So how do you actually do that? So this is really where Bell comes in. So Bell really invented the way of doing this. Building off of Einstein and Rosen and Podolsky, but I would say Bell really hammered this down for everybody. So the classic way of thinking about this is the following. So I'm given a state rho. So this is the density matrix. This is a little general way of writing it. You can think of rho as just the wave function. Okay. And the question I want to ask is the wave function of the two masses, so the two masses are A and B, is the wave function a product? Meaning all of the information in A and all the information in B has only classical correlations. That's what that would really mean. A non-example of that would be like the singlet state of two spins that you learn about in quantum mechanics. So what Bell basically showed was that if you, for example, take two qubits, there's some quantity W, which in this example is some product of the spin of the one guy and the spin of the other guy if you're doing two qubits. There's some operator whose expectation value will be positive if the state is not entangled, and it will be negative if you're in a specific entangled state. So that's kind of a lot to swallow. What this basically says is, if two systems are entangled, then there's going to be some correlation. So this expectation value, this is a correlation function of these two operators. You might hear some scratching in the back because my cat is randomly running around with a spring everywhere. What's going on here is in the excuse me. So if the state is classical, if it's not entangled, there will be a certain level of correlation allowed by classical mechanics. But in quantum mechanics, you can have correlations between two objects which are actually stronger than anything allowed by classical mechanics. And Bell makes that very precise by local hidden variable models, but this is the essential statement. So when doing a Bell test, what you want to do is try to prepare your entangled state, measure some operator like this, and check if the correlations violate one of these classical correlation inequalities. And that's basically exactly what we're going to try to do. So how would you do this in gravity? So this is a beautiful idea. So this proposal really was done by Sagata Bose's group in London in I guess 2017. Time flies. There's some earlier work that this is closely related to by these people. This really goes back to Page and Gelker in the 80s. But these guys gave a nice, like, pretty concrete proposal. So what do they suggest? So they say, okay, what do we use for the masses? We make them little diamonds, and these diamonds have a nitrogen vacancy center. So these exist. These are very useful for many things. But for the purpose of this talk, what it is it's just a piece of mass, and these can be pretty big, like nanogram. And then mass has little spin half in it, and the spin half couples to the motion of the diamond. So you can move the center of mass of the diamond around by hitting the spin. So in particular, what that allows you to do is say make a superposition of the diamond by just shooting this thing through a Stern-Gerlach experiment, because the magnetic field in the Stern-Gerlach will couple to the spin and therefore couple to the mass. And so what they propose is take a pair of these diamonds and take each one of these diamonds and shoot each one through a Stern-Gerlach apparatus. So now I have a diamond here superposed in two places. I have a diamond here superposed in two places. I let this thing free fall through my lab to get rid of noise. Okay? As it's falling, these things talk to each other gravitationally. And what you can work out is that the wave function of the two diamonds becomes entangled. So mathematically, it looks like I start them both in some initial state. I call it left here, I guess. And then as they go through, you become some entangled state where you have superpositions of they're both on the left, one's on the left, one's on the right, and so forth. And you can see that sort of the amount of entanglement is captured by some phase that shows up. And this phase is given by exactly the same scaling I showed earlier. So it can be sort of order 1, meaning visible, with nanograms, microns, seconds. Then what happens is at the end, you have this entangled state of the two diamonds. Okay? And what you can do is now test this entanglement through literally a Bell test, the Bell test in the typical sense with two spins, because you have spins in each diamond. So this is really a beautiful implementation. I mean, it's a very conceptually simple, in some sense, probably the simplest conceptually way of doing this. And that's fantastic. Okay, the problem is the numbers you need to actually do this. Okay, so to actually do this, there's a number of difficulties. One is that you need to measure both systems. So a Bell test, even with spins, was originally challenging. You have to measure two systems at exactly the right time, and you have to do it fast enough that there's no faster than light signaling and so forth. In this system, the entanglement is extremely weak, and the system is noisy. So you're really trying to extract a tiny, weak violation of the Bell inequality, that is sitting around in some very noisy system. That's okay. What really makes this hard actually is more mundane experimental issues. One is that I need a huge magnetic field gradient, and that's because I need a magnetic field gradient to operate the Stern-Gerlach to split the wave function. Maybe even, and by very large, I mean a few orders of magnitude bigger than anything that exists currently. Even harder probably is you need a pressure. You need environmental isolation, which is exceedingly good. So a few orders of magnitude lower pressure than, say, interstellar space. So I don't mean to say that you can't achieve these. People are for sure working on these things for many reasons. But this experiment is some years away from being done at best, because of these issues. So it's a really nice concept, and maybe it will be the way we learn that gravity is quantum mechanical. But I think at this point, it was worth thinking through. Maybe there's other ways of doing this. So I want to briefly mention a way that we've proposed. This is really the only slide on my own work here. This is an idea that Jake Taylor, Holger Muller, who's an experimentalist at Berkeley, Jake's a theorist at Maryland. This is something we had, which we think would basically eliminate all of these technical difficulties. So it's got a fancy name. We call it interactive information sensing. The experiment in some ways is simple, and the interpretation is hard. So the experiment, let me just describe what we would actually do. Okay, so the experiment proceeds like this cartoon. So what I do is I take a massive pendulum. So this can be like those sort of milligram scale Hertz frequency pendulums I showed you. I just hang this thing there. And I take an atom and I prepare the atom in an atom interferometer. So an atom interferometer is something where there's a laser field and I can put the atom in different wells of the laser field. So in particular, what I can do is I can take two wells of the laser and I can put the atom in a superposition of two positions. So this is just a Schrodinger's cat. This is exactly the same as these superpositions of the diamonds. It's just now with a very tiny system, an atom. Since with a very tiny system, I can actually imagine this atom sitting there for a long time. And in Holger's lab in Berkeley, he keeps them there for on the order of a few seconds, okay, in this nice quantum superposition. Okay, so now what do you do? So you take the pendulum, you put it there, say in the ground state, you put the atom, you prepare it in a superposition of two locations. And now what happens? Well, if the atom is on the right side, the interaction gravitationally between the pendulum and the atom will be, to move the pendulum to the right. And if the atom is on the left, the pendulum will want to move to the left. Okay? And so that's what's shown in this picture. So there will be some extremely tiny, but finite motion of this pendulum. And the pendulum will swing just very slightly one direction or the other. And now what this really does is it displaces the equilibrium of the pendulum. And so what happens is now the pendulum will sort of swing with the period set by the pendulum. And the idea is to wait for different amounts of time and measure the state of the atom. So why? What's happening is, as this evolution proceeds, here in this middle picture, I have an entangled state of the atom and the pendulum, right? The information is shared and the whole wave function of the universe is in two branches. Pendulum goes to the right, atom on the right, pendulum goes to the left, and atom on the left. While these are entangled, if I look at only the state of the atoms, what I'll see then is a collapse of the wave function of the atoms. This is called decoherence. It's a very well understood phenomenon by now. There's many experiments sort of like this, just not with gravity, where you see exactly this. I generate some entanglement between two objects. I measure one object and I see that its wave function has decayed. So concretely, you would see a loss of contrast if you do an interferometry experiment with this. But for the purpose of this talk, the main point is you only have to measure the atom. You don't have to do some horribly difficult measurement on both things at the same time. The fact that you're only measuring the atom and the fact that everything here is periodic in time with a slow frequency is what really basically enables this to be hopefully done. Okay, it really will eliminate a number of technical problems. So for one thing, okay, so let me. Good. So what's the real statement here? Is this really like a kind of a Bell test? Basically, the answer is yes, although you have to make a few caveats. So I wouldn't try to read this theorem. I just showed this to say that we made it precise. The basic statement is that if you see in this atom the collapse and revival of its wave function, and you know that it's happening because of the pendulum in a precise sense, then you can show mathematically that this is only possible if there's entanglement being generated and then destroyed and then generated and destroyed. And this has to do with monotonicity arguments and so forth. But essentially the output though is that what this means is that you can sort of do a Bell test in the system. So instead of measuring two systems at one time, I measure one system at multiple times. And I have to make some then assumptions about the interaction, but very weak assumptions. So essentially, this is a Bell test. It does essentially the same thing as the previous experiment, but it is substantially more robust to noise. And the reason it's more robust to noise is because superpositions of large systems, quantum states of large systems, die. They're killed by environmental noise very rapidly. Here we make a very tiny superposition of this mass. It barely moves. So actually this thing can barely be destroyed by the environment. What we really need is a long atom time, a long atom coherence, but this already exists. So we were sort of using a different technique, and I'll flash this slide. I think you should probably read the paper if you want to see sort of really the experimental details about why we think this could work. But I'll just say the punchline is this looks like you should be able to do it. So what you need is an atom interferometer with, say, 10 to the 8 atoms. So I draw it with 1 atom, but really you have a little cloud of, nearly 1 billion atoms. But these exist all over the place now. You need the atoms to be around for about a minute. So this is maybe an order of magnitude longer than state of the art, but nothing crazy to propose, building. And the point would be, these numbers all are just to say, at room temperature, so you don't really need a lot of isolation, you can, on paper, do the experiment. So Holger's lab at Berkeley is starting to seriously think through doing this, but we're quite excited that maybe you could do this experiment in the reasonably near future. Okay, so just to finish, I think I heard 40 to 45 minutes, so I'll just last 5 minutes or so. I want to circle back to my own natural state, which is theory. Okay, suppose we did these experiments. So maybe we do ours with the atom and the oscillator. Maybe we do the Bose et al. with diamonds. There's been a number of other proposals that are related. Somebody's going to do one of these sooner or later. And if they're successful, we can show quite robustly theoretically that what this demonstrates is that gravity is causing entanglement. Gravity can generate entanglement. That's the concrete experimental state. So the question now is, okay, who cares? Suppose you knew that was true. What did we learn about gravity? I mean, okay, it entangles things, very cool, great. Did I learn anything about the graviton? Did I learn anything about the string? Did I know if Penrose's thing about the wave function collapsing is true or not? And so that's sort of, I want to sketch what is known, the partial answers to these questions in the last couple minutes of the talk. So I mentioned this before, and I like to start with this. The first thing to say is that you can imagine ruling out some funny models. So I talked about the semi-classical gravity model, and let me just say it again. Semi-classical gravity would mean the metric responds to the quantum expectation value, the average of the stress energy of the matter. And I made the argument before, which is that this has no quantum information in it. This has deleted all the quantum information. That's in fact why you take the average. You don't want to deal with the quantum information. But if the universe really operated under this equation, you would not be able to see entanglement through gravity. So you would do the experiment, and what you would find is that the masses never get entangled. Now, it's hard to say for sure that you've done that, because if you never see them get entangled, probably your experiment just wasn't quite good enough yet. Okay, but so you'd have to really convince yourself that was the answer. On the flip side, if you did see the entanglement, this model is just out. It doesn't make any sense. Okay. This model has theoretical problems also, but that's a whole other talk. There's a kind of more modern and I think interesting thing, and this is an open question, so I would encourage people, young people, especially now that I'm getting old, to think about this. There's this idea that gravity is an emergent phenomenon. So this can actually mean a lot of things. And so let me give two sort of pictures here. So the first one is in string theory, there's the ADS-CFT correspondence. And there's a whole lot of story about that. But the short story is, okay, what if gravity emerges in that way? Gravity is some long wavelength version of string theory. In that model, we know by construction that the answer is, it goes as follows. At high energies, you have strings. At lower energies, you have gravitons. And therefore, by everything I said already, you'll see the entanglement. The gravitons will just mediate a Newton interaction and so forth. So if you do the experiment, it doesn't mean string theory is true. But if you do the experiment and you don't see the entanglement, I guess you would rule out string theory. That would be one way of saying it. If you did see the entanglement, it doesn't mean that you can go back up the chain, though. So this is one way gravity would emerge and basically give you the entanglement. You can imagine, though, that if gravity emerges, if it's the long wavelength limit of a hydrodynamic model with lots of little degrees of freedom, and if you took a typical model like that, you would actually expect that there would be no entanglement. You'd have lots of little particles of whatever makes up the gravitational field, hitting these objects. And so if you tried to entangle them, that would just destroy the entanglement. They would be like gas. You picture like gas hitting your system. Gas destroys all of the quantum information. So, this is a very heuristic. There's no paper that really goes into this. You need a microscopic model. But I do like to suggest that, maybe these entanglement probes are a way of sort of thinking about distinguishing ways that gravity could emerge, by characterizing whether or not they can produce entanglement. But really, in my heart, what I want to know about is gravitons. My prior is the graviton exists, and what I'm doing here is I'm proving that it exists. That would be what I'd really like to claim. But that's a high stake claim, and you have to be very careful if you're going to say such a thing. So let me show you, to finish, just what is the statement about gravitons in these models, in this experiment, okay? So what is for sure true, and I've said it a million times now, is that if the graviton exists, it will generate the entanglement, okay? And it's easy to picture how it happens. You have the two masses, you superpose one, gravitons fly around, everything is quantum mechanical and beautiful, works just like quantum electrodynamics. And I get the entanglement. So you might think then, if I saw the entanglement, that this would mean that the graviton exists, but this is wrong, right? The implication is only from the left to the right, not backwards. So you have to actually ask this question: if I see the entanglement, do I necessarily know it's a graviton? And really what you want to say is, under what assumptions would I know for sure that it's the graviton? Okay, so there's some partial results, but this is an open question in my opinion. So here are some partial results. So if you see the entanglements in the experiment, there's this beautiful paper by Alessio Balencia and a bunch of people, Bob Wald included, which shows the following thing. Suppose you can do the experiment. What you know for sure then is that you can generate entanglement with the Newton potential, the 1/r law. Okay, so that's a non-local force, and so that would mean that you could actually potentially signal faster than the speed of light. So that would be a problem. Okay? So how do you resolve the problem? Well, you have to assume something beyond just entanglement through the Newton interaction. And they show in the paper that if you assume that there's quantized metric fluctuations, roughly speaking, little gravitons, you'll resolve all of these faster than light problems. And indeed, this is the way, sort of typically you think about resolving faster than light problems. You just put quantum fluctuations. There's another related paper, which is a similar statement. This is much more recent now, where they basically show that if you see the entanglement, then you know that the force cannot be mediated by a classical degree of freedom. So you would say rule out some weird model where there's just classical gravitational waves somehow doing all these interactions for you. But none of these are really nail in the coffin. You do the experiment, you see the graviton. You can imagine finagling with, messing with these assumptions. You can imagine a model that would get around these. So, I put this as a conjecture. And in fact, this can, okay, so the conjecture, really the kind of statement you want to make is, in any field theory where you get the Newton interaction at low energies, that field theory definitely has a massless spin-2 state, meaning it has the graviton. So you'd really like to show something like this, and this is an open question. So certainly I work on this from time to time, and I'm sure other people have thought about it. It's not a simple problem. In fact, the answer is probably wrong. For the sort of connoisseurs in the audience, there's an interaction you can imagine which would mimic all of this graviton stuff, which is a scalar graviton. You can imagine a scalar field which couples to the trace of the stress tensor. And I think that would actually probably do everything else that's in this paper. That would reproduce the entanglement generation in the experiment. So it's kind of an interesting question. Do we know that the graviton exists if we get the entanglement? I mean, morally, probably yes. But formally, it's really not proven, I would say, at this point. Nevertheless, this is sort of why I'm doing this. I want to say, can we, you'd like to say that we've sort of come around, we've answered Dyson's question. So can you detect the graviton? No. Can you do an experiment where it would tell you that the graviton exists? Yes. It's kind of an interesting philosophical position if you wind up in the end. Well, we know that the graviton exists, but we can't directly detect it. So does it exist? I don't know. I mean, that's one for the philosophers. so good. So I'm out of time and actually did this on time. So let me just conclude. So again, if you zoned out through a lot of that, the statement is in some way simple. If gravity is quantum mechanical in the sense that it's a quantum field theory, if you want to be really precise, then the statement is that space-time perturbations, metric perturbations, are truly a quantum degree of freedom, just like the electromagnetic field. Then you can generate entanglement between two masses through the gravitational interaction. And then really the more bold claim in the talk is that you can actually test this question. You can get a binary answer: is this true or not? And you can do it with tabletop experiments in the reasonable near future. And so I'll leave some open questions. One is this one I just went through. If we do the experiment, we see the entanglement, we're sure it's from gravity by ruling out all the other possibilities and so forth. Do we know that graviton exists? And just again to hammer in that this is really an open question. For sort of more high energy people, you can think about gravity in 2 + 1 dimensions as an interesting counterexample potentially, right? Gravity in 2 + 1 dimensions has no graviton, and yet you can definitely entangle masses. So think about it. And then there's another question, which is there a smarter experiment to do? Nobody's claiming that we have the optimum thing at this point, and there's still time to make something before anybody actually achieves one of these things in a lab. So I put this reference here. We wrote a long review paper a couple years ago, which goes into a lot more detail about the models, the various types of gravity that you could test and so forth. And I would recommend you to check that out if you're really interested in this. In the meantime, thanks very much for having me, and thanks for listening to this talk.
Thank you very much, Dan. Now we're going to spend some minutes with questions. While we check if there are any questions on YouTube, I do have a question that Roberto, who had to leave early, has for you. He asks, can the quantum behavior of gravity be nonlinear? And in that case, would that feature make it harder to use the standard model or the standard quantum mechanics to build experiments?
Yeah, this is a very interesting question. This is a very nice question. Yeah, thanks. So I think I even put a backup slide for this. So the answer is maybe, and yeah, this is interesting. So let me first actually show so there are these semi-classical models, right? So this model actually is not well defined by just this equation. You might wonder, okay, well, this tells me how the metric evolves, but how do I know what the matter does? The matter, there's a state of the matter, and the state of the matter has to evolve under some equation, and like, okay, what happens? And in fact, if you put this thing in, if you assume the Schrodinger equation, this is a horribly broken system. It has superluminal signaling and all kinds of stuff. So in fact, the only way to make sense of this, and this is a recent sort of idea, is you have to make quantum mechanics nonlinear. Okay, the quantum mechanical evolution has to be nonlinearized. So this is a slide, and maybe I don't have time to go through everything on here, but this is a concrete proposal to do that. So now what you do is you say quantum mechanics, in addition to the Schrodinger equation, that's this first line, has these extra terms. And what these extra terms mean, these are nonlinear terms. What they mean is basically that you think of gravity in this model as measuring the matter, doing a computation, which is going to tell gravity, the computer that is gravity, how to move objects around. And so these terms are basically a noise. So these are an inevitable source of noise in a model where gravity would be classical coupled to quantum matter. And you can show that, this makes sense theoretically. It won't have superluminal signaling. It won't have any, obvious terrible problem. However, then it makes the test different, as the question was hinting at. Now you have a nonlinear quantum mechanics, and we know things happen in nonlinear quantum mechanics. So in particular, for example, these noise terms will cause heating in systems that you wouldn't expect. Right? It'll cause some irreducible heating rate of anything. And so you can start asking, like, okay, we have very sensitive systems, they're cold for a long time. Can we rule out this heating and therefore rule out these kinds of models? And this is a whole thing. Lots of people are writing papers about this right now, actually. So it's quite an interesting possibility, I would say.
Thank you. Any question from the audience here?
I have two ill-posed questions. Thank you, Dan, for that nice talk. The first one is like when you say these type of experiments might be performed in the near future, could you please define what you mean by near future?
Yeah, I mean, it depends basically how optimistic I'm feeling on a given day. So I would say that, this experiment, this sort of original proposal, one of the people in this paper is Andy Garaci, who would probably be actually doing a lot of the experiment. And he told me, if it's done in his lifetime, he'll be quite happy. So I think they're thinking, 10 plus years.
I see.
That's because you need these low vacuum pressures and stuff. So now to put my optimist hat, and obviously this is biased, this thing, we think you could do it now, a few years. It depends on a lot of details that we don't understand about, horrible things like the noise from the surface fluctuations and heating and Casimir forces and stuff. But at least order of magnitude level, this looks like something we could do a few years, let's say.
Thank you. And then also regarding this slide, sorry, I got lost a little bit, but
sure.
But I was thinking, like, if you prepare this entangled state, I mean, when you measure, you collapse it. So I was thinking, like, and actually this is, well, you argue at the beginning, it's a microscopical, let's say, experiment, but it's still big in that sense. So my question is, could you please repeat again how this will work? Because I think, like, as soon as the pendulum starts swinging, then you just lost all the quantum mechanical behavior, I would say, or I would think, because the wave function will indeed collapse, and then you just measure, and then, I don't know. Could you please go over this again?
Sure, yeah. This is a little subtle of an experiment. So, good. So you prepare the atom in the superposition, the pendulum starts moving. And I drew it this way because this is exaggerated, but the pendulum really barely moves in one way or the other. So if you think about it as wave functions, the pendulum's wave function, just barely doesn't overlap. Okay. And so then this causes, if you now measure just the atom, that will cause a tiny amount of decoherence in the atom.
Oh, I see. So it doesn't collapse like that. Okay.
So that's yeah. So I didn't explain this picture, but that's what this graph means. So this is saying sort of the atom's coherence, if you want. It starts at 1 in some units, and then it goes to some small value and back up, and this value is set by the Newton constant. So it's a tiny, this is a highly exaggerated graph.
Yeah. Okay. Oh, thank you.
Sure.
I have a question that is probably more philosophical. So let's suppose that instead of having a graviton, right, the real theory of quantum gravity is really just that space and time are discretized, and then we go into the realms of theories like loop quantum gravity or those things. So you wouldn't measure anything, right?
Wow, it's a hard question. I don't know if anybody has precisely stated anything about this. So, you'd have to actually calculate it. It would depend on the detailed microscopics, and in a way, I mean, it's not the same model, but it sort of gets into this statement. I can say that Carlo Rovelli wrote a couple papers and is very interested in these experiments. And he wrote a paper saying that, his expectation is you would see the entanglement, and loop gravity would predict that you would see it, and so forth. So according to him, at least, I think that's the statement. How exactly that works, I'm not sure. If you imagine that the space-time is just sort of broken up into little discrete chunks, though, I mean, to me, that would suggest sort of you might have some anomalous heating. It seems very hard to view that as like a coherent quantum system, but it should be studied in more detail, probably.
All right, let me check. Do we have?
I have one question regarding your the last discussion with Alejandro. Maybe you could go back to that slide. Right. So this is I find it very, very interesting. I mean, the conversation you just had with Alejandro, because initially when I saw this, I thought it was some kind of like quantum Cavendish experiment, right? Initially, I thought that you would be measuring like a displacement of the pendulum, but the whole point is that you're not, right?
Yeah.
The whole point is that I mean, I don't know if it's possible to measure that, but that you're not measuring the displacement, the oscillation of the pendulum. And that fact is what gives you this the coherence and recoherence, right? This kind of interaction with the pen. Okay, great. So then, in that sense, what are your main sources of background when you're doing this experiment?
Yeah. So this is a difficult question that we're still thinking through, and probably will require the experiment to be built to really know the answer. I can say things that we worried about and why we don't think they matter. So the sort of obvious things, if you know, in the lab, you imagine this is a real piece of metal and an atom and lasers. Okay. So what are the main problems? You know, you would have gas particles hitting everything.
Right.
That's obviously a problem. Maybe more importantly than the gas is you would have blackbody photons everywhere. And both of those things you would normally worry would be a problem. So if the pendulum was superposed, say, in a large superposition, that will be a huge problem. Anytime a gas particle hits it or a blackbody photon gets absorbed or something, that will just destroy the experiment. In fact, this is kind of like the under the hood, the amazing thing about this is, you know, the superposition here, the distance is like 10 to the negative 18 meters or something. It's a very tiny superposition, and it's much smaller than the wavelength of any of that stuff. So if a blackbody photon hits it, the blackbody photon can't actually tell where the mass is, if you want. It can't cause any decoherence. So in that sense, those noise sources don't actually, in principle, affect this. I think the more realistic problems are more annoying. You know, there are things like I can't put the atoms too close before there are interactions between the surface of the pendulum, you know, which is some metal, say, and the atom,
right?
Things like that. And so that, you know, really sets some design parameters, like you have to put the atoms at 100 micron at least, and things like that.
Right, because you have the Coulomb interaction at the end.
Right? You know, exactly. So, right. So, you know, luckily atoms are remarkably neutral, it turns out.
Okay.
You have van der Waals interactions, you know, you have to really, so these are pretty, yeah, there are things like that depend on sort of the details of the realization.
Yeah, because I was thinking about the previous experiment, the one that is like the Stern-Gerlach.
Yeah.
And there you can more or less like control the backgrounds in a way, because you can send one diamond only, right? And then send the other, right? So then I can imagine, okay, you can reduce some background there, right? But on the other, in the other one, I wouldn't know how to
so
like
here,
remove the background effects.
So one analogy with that is what you could do is, you know, you can just operate the atom without the pendulum and vice versa to get rid of some things. But I do agree, yeah, in some way the backgrounds here are going to be harder. The thing though with this is, yeah, you can understand the backgrounds. However, the signal itself will be destroyed in the experiment. This is what I mean by you need very low pressure. And this is related to this comment about blackbody photons. You know, as this proceeds, you're talking about nanogram objects separated at 100 microns or something. And that is an extremely unstable quantum mechanical system. I mean, a gas particle hits that and that superposition is gone. And now you have a classical ensemble and you'll see nothing. So yeah, I just to say, that's a really fundamental challenge in a setup like this.
Right. No, thank you very much.
Sure.
I have another question, Dan. So when you are getting to these so sensitive experiments where you can measure those type of distances, won't you end up measuring maybe some other new physics, or I don't know, a dark matter particle hitting your system, and that's massive? So
that's right. So actually, this system in Holger Muller's lab is originally designed as a measurement of fifth forces, you know, new light degrees of freedom to couple a mass to to the atom. So in fact, we're really piggybacking technologically off of that, and this would just represent maybe an order of magnitude better sensitivity in some way. So yeah, you can definitely imagine using this to look for new things. So fifth forces are a typical one. You know, we have done lots of work on looking for dark matter with this kind of stuff. Yeah, you know, this signal is kind of unique. This is a very, you know, human engineered signal, if you want. You really do a lot of controlling quantum mechanically, and so it's hard to imagine something randomly doing this, which is an advantage actually. But the systems in general, yeah, indeed, they're so sensitive. Looking for new particles is obviously something I do in my spare time now with these systems. Definitely a lot of things to be potentially could be seen.
Excellent.
Can I ask
Any
a
other-
question?
Yes.
Yes. Well, first of all, I apologize for coming a little bit late. I was lecturing, and so I got, I would say, less than half of your talk done, but still I find it fascinating. Thank you very much. So first a comment and then maybe a question regarding this last point of finding new physics. I can imagine Holger also, maybe he thought about doing some like equivalence principle check, because maybe you can arrange your atom you have there in the probe and try to build the charge conjugate version of that and see if it couples in a different way gravitationally to the pendulum. I don't know. Maybe they've thought about that idea, but that's a crazy thinking. That was my comment. And the question was regarding this experiment with the pendulum. All you care about the pendulum is its mass, right? You don't care very much about its constitution or what kind of mass. Is that right or not?
Yeah, that's exactly right. You need that it's periodic system. Other than that, it doesn't matter formally.
Okay, because I was wondering, because one of the problems regarding the noise, I think you mentioned it briefly, was not only the Coulomb interaction. I guess that those scales, which are very tiny, a Casimir interaction might spoil and be very important there. So maybe it could be a good idea trying to explore some kind of a pendula that could somehow shield you from the Casimir interaction. Would that be a good idea? Do you think?
It would. Yeah, definitely. So I'd be curious to know if you have in mind a way of making the pendulum specifically to do that. What people have done and what we assume we will do is put a shield. I wish I had a slide for this, but there's a nice experiment in Vienna last year which does exactly this. So what you would do is, in this picture, you literally put a superconducting sheet between these things, and you can use that to screen the Casimir force to some level. You know, the other thing you would do is, of course, you just put the atoms far enough away that, you know, the Casimir force goes down like 1 over r to the 6th or 7th. And gravity's 1 over r. 4? Okay, well,
4, yeah.
Okay, so, but, you know, with some much sharper scaling than the gravitational force. So there's some distance, and okay, in the dumb way of thinking, in my way of thinking, you know, you just put the atom far away enough, you don't care. But yeah, in practice, you would shield it. I do wonder if you have some idea for what you can do to the pendulum itself.
I think I might, but I would need to read in more details. I don't know if in your papers you have information about this. I will look at it, but I do have some idea. But still, it's I don't know if it's feasible to construct a pendulum like this. It's regarding to these new states of matter. Topological insulators in particular. There are some proposals in which you could tune the Casimir force between different materials, actually either making it repulsive or attracting. So that's could be interesting.
I did not know that. Yeah, I'd be happy to talk about that actually. If you maybe can email
I
me.
will look into your papers and send you an email about it.
Yeah, great. Thank you.
Okay, those were my questions and comments. Thank you very much.
Thanks.
All right, so thank you everyone over YouTube for watching this seminar, and we encourage you to subscribe to all our social networks and follow us to be up to date for the next seminars. And we once again thank Daniel for this amazing seminar, and we'll see you all soon.
Thanks again.